So, we showed with two examples how magnetic vector potential can be obtained if the current densities are given, and if we can find a corresponding charge distribution for which the electric potential can be written easily, then that same expression transforms into the expression of vector potential. And all this is because of the mathematical similarity of equations governing electric potential and components of magnetic vector potential. To once again tell what it is Laplace equation. Del square of electric potential is minus rho over epsilon naught, and del square of Ax, Ay, Az are similarly here it is mu naught times Jx. Del square of Ay is minus mu naught of Jy, and del square of Az is minus mu naught of Jz. So, each of these has the same mathematical structure at it is here. The difference is constant. Here 1 by epsilon naught, if you replace by mu naught, you get identical mathematical structure. So, to get this Ax from given current density x component, you assume that this is a charge density, write the electrical potential, and then that same expression gives you Ax. Similarly, for Ay, Az, and you get the complete magnetic vector potential. So, we will take one more example which is otherwise very complicated. Griffiths has solved this in that book Electrodynamics, but we will be using this and will solve it in a different way. And the problem is you have a sphere, and it contains surface charge density. It contains a constant uniform surface charge density, and that charge density is sigma. Let us say it is sigma. Radius is r, and then it rotates about a diameter with a uniform angular velocity omega. Rotates about a diameter with uniform angular velocity, and that is omega. The direction is this diameter, and you can take it z axis. So, this is rotation axis, and the whole thing is rotating with omega, and you want to know, you are asked to know the magnetic field inside and magnetic field outside. So, we will first solve magnetic field inside, we will get vector potential inside, and then curl of A, from there we will get that B. So, that is the game. Now, what is the current density? First thing is that it is a surface current. The charges are on the surface of the sphere, and then the sphere is rotating. So, those charges at the surface, they are moving, and therefore, there is a surface current density. And you know, surface current density, the magnitude is sigma times velocity v, right. The volume current density is rho volume charge density times v, and so on. for a linear current it will be lambda times V, like that. So, we will have to use this one. So, if I take a point here on the surface, and then this is x, y, z, or it is r, theta, phi in spherical polar coordinates, and then this will be going in a circle of certain radius. I can take this point as well on the board. So, this is a surface point. So, this is also a surface point. So, let us do geometry will be easy. So, this will go on this particular circle. This will be the radius. If this angle is theta, that is the coordinate theta also, r sin theta. This radius is r sin theta. Okay. And this length is r cos theta. Z is equal to r cos theta. You remember that transformations, Z is r cos theta. Then if you take the other side, one component is this side, one component is on xy plane, then the magnitude of that is r sin theta. Then you multiply by cos phi, you get the x coordinate, you multiply by sin phi, you get the y coordinate, cos phi here and sin phi here, right, and z is of course r cos theta. So, the current density, K, it's sigma times V, and V will be omega r sin theta, because it is going in this circle. This charge which is here is going in this circle, and the radius of that circle is r sin theta. Therefore, the linear velocity V will be omega times radius, and that is r sin theta. So, this will be the magnitude of K. And what is the direction of this K? What is the direction of this K? This is rotating this way. So, everywhere the direction is like this, and this is phi cap direction. This is phi cap direction. So, K is in phi cap direction. Our first task is to write x component, y component and z component of this current density, so that we can use these equations. So, what is x component, what is y component, and what is z component? Z component is 0 of this phi cap. Unit vector in this direction, unit vector in this direction, unit vector in this direction. If this is vertical, this phi cap is always horizontal. So, the z component is always 0, and the x and y components will be there, and we had done it in the previous lecture itself. This phi cap will be, okay, let me see if I remember it correctly, cos of phi and in j cap direction, and minus sine of phi in I cap direction. Okay. We did it in the previous lecture. If you go back and see, we have used this quantity. So, this phi cap you can write as this K is now sigma into omega into r. This is constant, sigma into omega into capital R. This is the radius of the sphere. So, that is always constant, sin theta, this will be there, and then into cos phi j cap minus sin theta and sin phi, and then you have this I cap, right. So, you can write now the x, y, z components of this current density. Kx is equal to, let us write this as C, capital C. Let us write this as capital C. So, it is capital C sin theta and minus here and sin phi. That is the x component, I cap here. So, that gives the x component. So, it is capital C minus sign here and sin theta, sin phi I cap. So, this is sin theta, sin phi, this is the x component, and y component ky, y component, j cap component. So, capital C sin theta and cos phi, this is y component and z component is 0. So, this immediately tell me the z component of vector potential is also 0. To get the x component and y component, the idea will be treat this as a charge density, surface charge density. This is surface current. So, this is surface charge density, where on the surface of this sphere, and if this is the charge density, what will be the electrical potential? But do I know it or can I know it easily? What will be the electric field, what will be the electric potential if you have a spherical charge distribution, charges on the surface of the sphere with this density, some constant times sin theta sin phi on some constant times sin theta cos phi. We have done this problem in our classical electromagnetism 1, and so I am taking it from the book. This is in the chapter of dielectric and polarization, and that is chapter 8 in this book, I believe. Yeah, dielectric and polarization, and I tell you the results. Field due to, okay, this is electric field due to uniformly polarized sphere. Okay. So, if you look at with this heading, electric field due to a uniformly polarized dielectric sphere. This is the heading, this or something like this, dielectric sphere. Now, let me give you some background, although it is electrostatic thing which you should read from the book, or if you know it well. The polarization of a dielectric material is, if you have a dielectric material, put it in an electric field, then the individual dipoles in the entire volume of the dielectric, they get aligned, and you obtain electric dipole moment per unit volume in the entire interior of this material. That is known as polarized dielectric material. Okay. So, this polarization is given by this vector P, which is electric dipole moment per unit volume. So, if you have some material and then you apply an external electric field, and everywhere inside you have this dipole moment, and then take some volume d tau and then see how much is the electric dipole moment here, divide by this d tau, that is the polarization at this point, and similarly for the entire interior. So, this P is defined. Now, it so happens that although there is an electric dipole moment here, but there is no net charge density in the interior of this material, it is still neutral. But on the surface you do get a surface charge density. When you put a dielectric in an electric field, on the surface you get a surface charge density. The total is 0. At some places it will be positive, at some places it will be negative. That is how that comb, that you take the comb through airs and then it attracts small paper pieces. So, it is because of this paper piece is a dielectric, and this comb, charged comb, produces an electric field. So, that paper piece, that dielectric is in the electric field, and then at the surface charges appear. The closer to the comb, that surface opposite charge appears, and the farther the similar charge appear, and finally there is an attraction. So, it is this phenomena of polarization that helps there. Now, this surface charge density that appears, that is given by P vector dot n cap vector. And what is this n cap vector? Now, I am on surface. So, suppose this is the surface, there is a point on the surface, right, here is surface, and draw a normal, outward normal, that is n cap. So, P vector which is there and uniformly polarized means everywhere is the same P, here also the same P, here is also the same P. So, that P vector dot product with this outward normal unit vector, that is the surface charge density sigma that will appear here. So, at different places you will have different n cap, and therefore, the charge density will be different. So, if I look at our sphere, and if the polarization is this way, if the polarization everywhere is this way, uniformly polarized, and on the surface you take some point, and then you draw a normal here. So, that normal will be in r cap direction, that normal will be in r cap direction. So, P in our case, this P vector is P magnitude which is uniform, and then dot or P vector is r cap vector. And what is the charge appearing here? The charge appearing here, that will be sigma will be, this is P vector and then dot r cap vector, because this n vector, the outward normal is same as that r cap vector. So, this is sigma. Another very interesting derivation which is there in that chapter, in this section, that is, if you have a dielectric sphere and uniformly polarized, then the charges will appear. If this is the case, then positive charges will appear on this side, negative will appear on. Remember, this is not circle, this is a sphere. Remember, half the sphere is in the classroom side, half the sphere is on the other side of the board, and I am talking of surface, this whole surface. So, on this side you will have positive charges, on this side you will have negative charges with certain charge distribution. The interesting part is, if you ask what is the electric field because of these charges, what is the electric field inside this volume of the sphere because of these charges which are appearing on the surface, that electric field is from positive to negative, like this, lines will be like this, and they are all in the same direction, they are all in the same direction opposite to the polarization vector P, opposite to the polarization vector P, and the magnitude is also constant, and that is E is equal to minus P vector divided by 3 epsilon naught. Very, very famous and interesting and important result, that if you have a uniformly polarized sphere, the electric field inside is just given by this minus P by 3 epsilon naught, and outside electric field is like a dipole, that is like a dipole, as if there is a small dipole at the center, and then the dipole kind of field will be there, but we will be presently talking of the inside only. Okay, so with this much of preparation, with this much of revision of electrostatics, let's come to our problem. Our game was to find a situation in which the surface charge density is given by this equation or this equation. In fact, we will need both. So, if I know the electric field because of this kind of surface charge distribution, then I will immediately write the electric potential, and that expression will give me the x component of magnetic vector potential. And if I can get a charge distribution of this kind on the surface of the sphere, and then if I can know the electric field, then potential, we will get the y component of this magnetic vector potential. How do I get a doable charge distribution of this kind on the surface? And very easy, very easy. Suppose you have this sphere and the polarization is uniform, but in this direction, j cap direction, y direction. A sphere which is uniformly polarized, but polarized in this j cap direction. What will be the charge appearing? This will be C, magnitude is C, j cap and dot r cap. So, what is this j cap dot r cap? What is this r cap? R cap is let us say r vector divided by r. Okay. At any point, r cap vector is r vector in the direction of r vector. R cap is always in the direction of r vector, and so it is this. And this is x I cap plus y j cap plus z k cap divided by r. And remember, x is r sin theta cos phi, y is r sin theta sin phi, and z is r cos theta. So, this x is r sin theta and cos phi, this much I cap, plus y is r sin theta and sin phi, plus z, this is j cap, plus z r cos theta in k cap direction, and this whole thing divided by r. So, it is sin theta cos phi I cap plus sin theta sin phi j cap plus cos theta k cap. That is my r cap vector. What is j cap dot r cap? J cap dot r cap, j cap dot I cap is 0, j cap dot k cap is 0. So, j cap dot r cap will be simply, so let me write sigma itself. Sigma will be this C, and this is that r cap dot with j cap. So, you will only get sin theta sin phi. So, sin theta sin phi. Look at this sin theta sin phi, sin theta sin phi. So, we have gotten a charge distribution which is this, except for this minus sign. So, it is this, and if I take my P vector as minus C j cap, the situation is even better. The situation is even better. If P is minus C j cap, then this sigma is minus C j cap dot r cap, and then you get a minus sign also. It is identical to this. For this charge distribution, do I know the electric field? Do I know the electric field? Yes, very much. This charge distribution is coming from this polarization, this kind of polarization. And if this is the polarization, here is the electric field. if this is the polarization, put it here and write the electric field. So, for this charge distribution, the electric field is minus P, and that is C j cap, that is C j cap. This P, here is P minus C j cap. So, I am writing here minus C j cap. So, it is C j cap divided by 3 epsilon naught. That is the electric field. That is the electric field. And if this is the electric field which is constant, this electric field is constant. So, I can immediately write the potential, very simple. What will be the corresponding potential? The potential will be minus C over 3 epsilon naught y. Why? Because you know that Ex is minus del V del x. There is no Ex, no x component of electric field. So, you will not have any x dependence in the potential. You will not have any z dependence on the potential, no z component, and for y, Ey should be equal to minus del V del y, and that is E in fact. So, minus del y of this, minus del y of V will be just C by epsilon naught. So, that will be the y component which is there. So, this is our potential, electric potential, because of this charge distribution, right. All these things I do not need anymore, will need it, but not now. So, let me make some space here. Now, I am back to our problem. I want x component of the magnetic vector potential, x component of the surface current density is known. I assume that this is a surface charge density. So, here is that surface charge density. I ask what is the electric potential, and electric potential is this, and nothing else I have to do. I have to only write this as the x component of the vector potential. So, Ax is equal to exactly the same thing, only thing that 1 by epsilon naught has to be written as mu naught. So, it is now minus C mu naught here by 3, okay, minus C by 3 mu naught and y, and how much is y? Y is this r sin theta sin phi. So, that is the x component of vector potential, and now you guess what I am going to do in next lecture to get the y component of this magnetic vector potential. I will need a surface charge distribution as C sin theta cos phi. So, we will manipulate our this polarization vector in appropriate way, so that this P dot r cap, P dot n cap, that gives me this expression, and from there we will again write the potential, and that will give me the y component of magnetic vector potential. Z component is already 0. Once we know x component, y component, z component, the vector potential is obtained.